So let's take a look at, for our case, what happened. We are interested in testing the coefficient for these three variables, okay? Hours, budget, and state, okay? And if I can write it, beta 1 is the coefficient corresponds to hours, and beta 2 is coefficient corresponds to budget, and beta 3 is the coefficient that corresponds to state. And right now we want to conduct the t-test on these individual betas to find out whether it is different from 0. What we do is we actually go to the last column where we find the p-value for the individual test. And for example, for the first one, this is 0.0015. That's a small p-value. It is actually smaller than our significance level. If we take 5% at the significance level, this is smaller than that. And for this one, what we can tell is beta 1 will be different from 0 based on the small p-value. Okay? If you look at the second one, this kind of depends. Okay, it kind of depends. If we're picking 5%, then for this case, beta 2 is not different from 0. It is equal to 0 because the p-value is not small enough comparing to 5%. And lastly, the p-value for the last one definitely indicate that beta 3 is equal to 0 because the p-value is not small enough at all. Okay. So if we take 5% as our significance level, what we'll find out is only the first beta, beta 1, is different from 0. And that indicates that only the first variable, which is hours, is linearly related to y. Okay, and only hours has a significant relationship with y. So if we are interested in changing or predicting y, which is the profitability, we should consider hours, which is the training hours, workforce training hours. Okay. Now, furthermore, based on the coefficient, which is 0.994, what we can tell is if the training hours increase by 1 unit, which is by 1 hour, we would expect the profitability to increase by 0.99 on average, holding others constant. Okay. So let's imagine this. If we are given this task based on the background, okay, and so your task is to find out what factors would affect the profitability, okay? You collect data on factors you think could potentially affect profitability, then you run the multiple regression analysis, get the coefficient, get the output, and then the next step is to determine seriously of all the factors you think could affect profitability, which ones are really affecting profitability. And to answer that question, what you really need to do is to do what we just did here, conduct individual t-test, basically look at the p-value for each one of them, okay? And if the p-value is smaller than significance level, then you would say, yes, that factor is significantly related to profitability. That factor is useful in predicting Y. Okay. This is probably the last part for up to our multiple regression analysis. That is, we still care about the overall fitness of the model. Although this time, we actually will not look at Rsquare. We used to say Rsquare measures how well the model fits the data. However, for multiple linear regression, we actually look at the adjusted R-square. In our case, that turns to be 0.67. And you would also notice that adjusted R-square is actually smaller than R-square. And that is true all the time. So we always will find adjusted R-square to be smaller than R-square. Okay? Then you may ask, wait a minute. If I look at adjusted R-square, that actually means my model is not as well as what's indicated by R-square. Well, that is true. And this also indicates some problem or issue with using Rsquare. Okay. The reason being, the R-square, the traditional R-square, will be inflated if we include more than one independent variables, that is more than one axis. Okay. Actually, for our model right here, we have 3 axes right now. Okay. If we keep adding more axes, what you will find is R-square is increasing very quickly, but adjusted R-square will not increase that much. And this doesn't matter what variables you include, okay? You could include some irrelevant variables, x4, x5, x6, etc., and you still find R-square to be increasing. That potentially means your model is improving, but really, is it that case? You are including several useless variables. Why should your model be better? Okay. So with that in mind, statisticians decided we're gonna need to create something. We're gonna need to adjust the R-square. And what we want to do is we want to penalize regression analysis using many axes in the model. And therefore, the adjusted R-square adjusts for the number of independent variables. Actually, the adjusted R-squares adjust downward when the number of independent variables increases. At the same time, sample size also matters. That's another shortcoming for R-square, because R-square doesn't really take into consideration of the sample size, but it matters. So adjusted R-square also adjusts for sample size. Now, in terms of interpretation for adjusted R-square, it's the same thing. It's the same idea. Adjusted R-square still tells us how much variation in Y can be claimed by X. So for our case, we can tell about 67% of the variation in profitability can be claimed by the model. Okay. And as usual, the higher the adjusted R-square, the better the model fits the data. So that's several things I would like you to learn about multiple regression. And I'm pretty sure you will learn more details when you take the STEP course later. What I want to do right now is to talk about our series data. Okay. Now, depending on the situation, you might need to estimate multiple regression as using your own revenue data. Okay. So what I want, sorry, not for this course, not for this semester. I just realized I shortened the data analysis project. So in the regular semester, let me just tell you why I'm saying this. In the regular semester, okay, I usually ask for the data analysis project, I also ask students to run multiple regression analysis following a similar routine of what I do with Sears data. Okay, but it's still worthwhile for us to talk about it. So with Sears revenue data, suppose that I'm interested in variables that affect Sears revenue. Okay, and at this moment, I will only consider macro data, macroeconomic data. Okay, among the macroeconomic data, I selected several of them. The first one is net worth. The second one is CPI, that's the Consumer Price Index. 3, GDP, which typo here should be GDP. And 4 is interest rate. Number 5, employment. And finally, I realized that Sears data involves strong seasonality, so I want to use seasonal dummies to control for it. Okay. So let me first talk about how we create seasonal dummy variables for our data. And I will need to switch to Excel. All right. So here's my Sears data. I've gathered the date of the data, revenue, net worth, CPI, GDP, interest rate, employment. What I want to illustrate now is about how to create seasonal dummy variable. Okay. So in Excel, if we want to create seasonal dummy variables, we're gonna do if clause. So we type equal to if, open parentheses, and we need to do the logical test. We want to look at this cell. That one, that indicates the date, and we want to check the month of that cell. Okay, if the month of that cell is equal to 3, let's assume that March the 31st belongs to the first quarter. So that's the data revenue for the first quarter. Okay, so we're gonna say if the month of observation is equal to 3, we decide that's seasonal 1, so we want the season 1 dummy to take a value of 1, otherwise 0. That's what we do for the create the dummy variable. If we close parentheses and hit enter, you will see that the season 1 dummy take a value of 1. Let's test whether it works for others. So again, you're gonna go to the corner of the cell. Once your cursor turns to the solid cross, you just drag it down, and the formula from Excel will ultimately be copied. So look, for the second one, since the month is 6, it's not taking value of 1, indicating it's not season 1. Same for the third one, same for the fourth one, and for the fifth one, when we have month equal to March, we find season 1 takes the value of 1. So that works. Okay. And for season 2, similar idea, we're gonna do equal to if, open parenthesis, and we ask whether the month of the observation is equal to 6. If that's the case, we want it a 1. If not, we want a 0. Okay, close parentheses. Okay, and let's do the same thing for the third one. We want the month to take a value of 9. That indicates it's the third season, otherwise it's not. Oh. It's just the formatting of the cell is not correct. That's why it's not showing a 0. There we go. Okay. So once we create the dummy for the first observation, we can just drag it down for the rest of the data to get the dummy for all of them. All right. Now, since we're already here, let me show you quickly how we run multiple regression analysis using Excel for our series data. What we do is we could go to data. And unfortunately, I'm not sure why it's not showing, but at the end, you should be able to see data analysis if you have it installed. Okay, so I'm gonna click on data analysis. Okay, there we go. Then we see this new window pop up, and what we're interested is regression analysis right here. So you just click OK. All right. Now let's define Y variable, which is the revenue. So I'm gonna highlight revenue data, the whole column. And next, I'm gonna highlight the independent variables. Since I have several of them, I need to make sure I highlight all the columns that include my independent variables. Now, by the way, most likely all your independent variables are side by side. But just in case if you have one independent variable that is not side to side to the rest of the group, you do want to copy and paste that column back. So there we go. I've got the independent variable taken care of. It's probably not shown correctly on your screen, but I did include a label when I highlight the data. So I do want to click label to indicate that I have labels in the first row. Again, I want the outputs to be on the same page. So I need to, well, let me pull it up. Okay, so there we go. Output range. I want to determine output range to start from this cell. So I just randomly click one empty cell and then click OK. So let me show you the output Excel produces. All right, there we go, finally. Okay, so this is a typical output from Excel using for multiple regression. What we would be looking at include right here. Right there, you see the adjusted R-square that measures how well our model fits the data. Right here, you see p-value for the overall t-test. So this is the p-value for overall, I apologize, overall f-test. Okay, in parallel, we have a very small p-value because it's 2.6 times 10 to the negative 16. That means you're gonna need to move the decimal 16 places to the left. That's an extremely small number. It's almost 0. So we're good with it. Right? And the next table will list the coefficient estimated as I will highlight the column. Okay. That's the column that gives us the value for the alpha and beta, the estimate for alpha and beta. And this column gives us the p-value if we want to know the individual t-test. In other words, if we want to know which variables we included are significantly related to y, we're going to look at these p-values. For example, this one, the one I just highlighted, is small enough for us to believe that net worth is correlated with revenue, sales revenue. Okay. In addition, you can tell that GDP, 2 lines down, is also highly correlated with revenue. All right, so let's switch back to our PPT file. Easier to look at that one. So now you see a similar page of what we just did. We created the seasonal dummy. We then run regression analysis. Okay, and I highlight a few things that we just mentioned. That's the adjusted R-square. That's the p-value for f-test. And these are the p-values that are smaller than 0.05, which is 5%. And that also means these corresponding variables are significantly related to y. Okay. Again, just in case you didn't follow how seasonal dummy is created, you've got the formulas here. Just type them in, okay? Hit enter, you will get the seasonal dummies. All right. So another situation, just to warn you, okay? One, if you try this regression, and if you pick several macroeconomic data and try the regression, you might find some confusing results. That is, you might find Look, I have a very small p-value for the f-test. That means my model is valid. But then when I look at the individual coefficients, okay, look at the individual coefficients, there's only one independent variable, which is sales, is highly correlated with Y. Okay, and for the rest of them, they are not significant at all. So you may wonder what's going on. Why not, according to the f-test model, is great, it's valid, but when I expect the variables to be highly correlated to Y, they are not. Okay, this is something women call multiculinarity. That's the potential cause of what the situation right here. So multiculinarity arises when the X variables, the independent variables, are highly correlated with each other. Okay, and this can be determined by looking at the VI, what's something called VIP, VIF. Sorry, the VIF usually tells us whether we have multiculinarity, and large VIF indicates multiculinarity. So if you take a look at the value for sales and labor, they are high, they are very high, 56 and 55. That means sales and labor are highly correlated in our model. Okay, this may happen if you try for your own revenue data. Okay, and that just means you got several independent variables that are highly correlated. Okay, in that situation, the possible solution is to drop one of the independent variables. That's really the best thing you can do. And which one to drop? Well, that depends. Typically, we're going to drop the less important one and keep the one that's important. In particular, if there are several variables that are highly correlated and you're trying to determine which one should drop, you should always keep the ones that you're interested. If you are interested in the relationship between, let's say, for example, for my Sears data, if I definitely want to find out the relationship between the revenue and GDP, and GDP happens to be highly correlated with some of other variables, I will definitely keep GDP and drop other variables. Okay, so that's the solution for multiculinarity. It's very common, but when weird thing arises, people just get lost and say, huh, what's going on? So it could be multiculinarity. Okay, so that's the end of the discussion for linear regression. And that pretty much concludes the whole semester. That's the very last lecture for our semester.